Well, might as well, just for a bit. Let's see, testing video. Let's see, test. Yep, there we go. So I'm coming through fine. There's no telling who else might jump into the stream. Let's see, so that looks good. Pause that, don't need to track that, don't need to track that. Everything seems good. Alright, well, what I'll do is I will start by taking some questions. I guess we'll download Prolog here while we're waiting. I think they're using. We'll go ahead and place any questions you may have in the text area in the chat, and I'll address them just so for the benefit of everybody while this downloads. Then I'll pull up Blackboard. For CSC 240. Okay, I got the Prolog live review. Let's see, let's go to homework. Homework 11 was still functional. Homework 12. It's Prolog, right? Not homework. Tutorials and resources. Prolog tutorials. Tutorial for Prolog. Right, the period at the end of the statement. Question mark right. Constant. Hello world, etc., etc. Fairly straightforward. Here we go, facts. Right, and build up more rules. Cool. Let's see here. Let's get the stable release of SWI Prolog. Interesting source for Prolog is available. Let's do this. Alright, so with Prolog it's fairly straightforward. Prolog, you just state your facts, and then you reason over your facts. So, for instance, let's look at this. So if I pull up Sublime, I'll pull up an example. Perhaps let's say we have a database with verbs. Let's say one of the verbs is weather. And then we use tuples, specialized tuples in Prolog. So we might say that the weather in Phoenix in the spring is hot. And period at the end is very important. We might say the weather in Phoenix during the summer is hot. We might say the weather in Phoenix in the fall is hot, and then we will say the weather in Phoenix in winter is warm. We'll also go on to say that the weather in Wellington in the spring is warm. And then if we do something like this, we can then write a rule. And the rule could be stated as such. We could say the rule warmer. We're going to define a rule called warmer. It takes C1 and it takes C2. And we're going to define that to be the weather in C1 in the spring is hot, but the weather in C2 in the spring is warm. And what this means is what we're saying here essentially is that if you define a rule called warmer and you give me a C1 and a C2, that means using our previously generated facts, if we plug C1 and C2 should cascade down into this rule right here and essentially be evaluated on its own. So essentially this comma is the AND operator. So this is logical programming. Everything is logically based. So because everything's logically based, we can do something really cool. We can now validate that if something's warmer. We can say, all right, so question, is it true that it's warmer? And if we don't use a period, I believe it's a statement, we can write, let's see here. I believe true means a match is found. Yes is a match is found. The search is completed. True, but true implies a search will continue. And then no is that the search is completed but no match was found. So we might say, question mark, we might ask, is it warmer in Phoenix than Wellington? And then the output would be something like that. Yes, it is. Because if we take the warmer rule, we plug in Phoenix, well, we look in our database and we see that the database contains weather, Phoenix, spring, and hot. Database contains that. It also, so this is an AND operator, also contains Wellington, spring, and warm. So then this resolves to true, or yes in this case. It's a logical database. Does everything logically. So now you can build very complicated logical structures here. We could do maybe something like, maybe we say colder, C1 and C2. And what would that mean? That would mean that the weather in C1 in the spring is warm and the weather in C2 in spring is hot. That's what we imply. So now, because that's what we're implying, and that's what we do, then we can also query Prolog and say, all right, is it colder in Phoenix compared to Wellington? And it will respond, no, it is not. That is not a true statement. And that's about it. So you essentially, I'll create a delimiter. That does not look pretty. Let's make it a little bit prettier. There we go. It looks a little bit prettier. So you'll see this is data, and we use Prolog to reason over our data. That's what we do. So you can create, and you can do this and this is actually very, there's databases that are reserved to functionality very similar to this. And as you continue, you can actually link this to anything. You can actually have much more complicated rules. So we could perhaps define we could perhaps say advisable C given S and given C1 given our current city. So let's call it current city. Let's call this destination city, and let's give it a season. So given, is it advisable to move to the destination in the season? If we are in a current city and we are in destination city, so then obviously the result would be we're going to pretend that it's advisable because we are Arizona natives. We're going to pretend the cooler weather is what we want. So that means that the solution would be colder in the dest city compared to the current city, and that would be it. Now note there's a quirk here. For this to work, we would have to modify colder now to take a season. So we take S, this would be S, and this would be S. We'll take S, this will be S, this will be S. So thus then we can continue on and say season. And now it will work. Otherwise we are going to get it could work, but we would always assume spring, and that's not very applicable to what it is we're trying to do. So we don't want to have to assume something that we're not assuming, or that we don't need. We want to give it the user the option to choose what they want. So then essentially what you can do is you can take very basic data and you can create a set of rules and you can query your data over the rules, and you're just specifying what. You're not specifying how, you're specifying what. And then the program will essentially take care of itself. That's essentially it. Now what I'm going to do, let's see if we can find a decent example. Let's try. There we go. Let's see if we can find something. Here we go. Prolog. So let's take a look at a Prolog tutorial on recursion. So what we're going to use is we're going to use facts as stopping conditions. So the fact will act as a stopping condition, followed by some rules that perform some operation before re-invoking itself. That's how we're going to do this. So what we'll do then is let's create now more data. Let's say we have data. Say we have some data, and I'm going to just put dot 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 because it's going to be some kind of data. I'll just put maybe curly braces. And I'm going to backfill it with more data. But let's say now we've got some new logic rules. Let's say that we've got, maybe let's say that our program looks a little bit different. Let's say our program's like this. So are we on route? Are we on the road to Rome? Where, being on the route to some place, we don't know what, implies that we move to the place using some method using the new place, and that we are on the route to the new place. And then we instruct the rule set to move home, taxi, Halifax, and we move Halifax, train, Gatwick, then we move from Gatwick, plane, to Rome. So now what we discover is that en route is a recursive predicate. So this program is going to see if it's possible to travel to Rome from a particular place. The first clause sees if we have already reached Rome, in which case we stop. The second clause sees if there is a move from the current place to somewhere new. And then the recursive clause sees if the new place is on the route to Rome, and then this continues. The database of moves that we can make is going to be the following statements right here. So these are the databases of moves we can make. So then a query might look something like this. Can we let's see. Let's see if we can find a good query. Let's look at this. Let's try on route Gatwick. So when we do this, this will unify with our second clause right here. Our second clause, which is this whole chunk. And we use the recursive clause to find some place new to go. So the goal will be to move from Halifax to some new place. And if this new place succeeds, well, of course it will, because we can catch a train from Halifax to Gatwick Airport. So the method will be train, and that will print. So as a result, we'll get an output that will give us the entire thing that we need. So if we're starting, let's say we're starting in home, then what will happen is this. It will print out something like this. Home to Halifax by taxi, Halifax to Gatwick by train. And there you go. Something like that. The string formatting may be arbitrary. But when you pose it, what you do is you have en route Gatwick, and what you can actually do, maybe we do something better. Maybe we do move. Can we move from home to Gatwick using some variable x? We don't care what the method is. Let's call it method m. So then what it will do is we want that to be a variable. Because if this is a variable, then it will print something like this. It'll give us the sequence. If this is not a variable, and we use something just like train, right? Well, then this will return no. It will return false because we have to take a taxi at some point. We can't do everything by train. So we leave this as a variable called m for method, and then it will actually print out what has to happen in order to for this to occur. And that's very useful. When you leave things as variables, you can actually do some really cool stuff. It lets you actually trace an entire database, which is good. You need recursion to be able to trace a database. So it's very similar to the imperative model when we're doing recursion. The only difference is now we are defining rules that use recursion to evaluate them. And it's all logic. There's nothing really new happening here. It's all happening strictly from a logical standpoint. So I'll take a second. If you have questions, go ahead and post them in chat. I have one more example that I can do, and then we'll take one more break for questions, and then we'll once again end early because we have a very small audience, and I want to maximize our time as an entire unit. And if we've got very few people watching the stream, then we're going to maximize our time elsewhere. But I do have one more example, so if you have questions, go ahead and post them in chat. I'm going to clear all this. So then I'm going to start my next example. The classic family tree example. Now you'll notice I'm defining ancestor twice. This is legal. This is equivalent to an OR operator. This means ancestor will return true and perform computations on the assumption of truth if at least one definition of ancestor is correct. Now this is actually really powerful. This is really powerful. Here's the reason why it's so powerful. Because we have said that an ancestor can be the ancestor of X the ancestor of X is Y. Okay? The ancestor of X is Y if X is a parent to Y. So X is an ancestor of Y if X is a parent to Y. On top of that, X is an ancestor to Y if, by chance, not only this, but if, or it's either this or this, that for some z, x is the parent of some z. And then for that same z that x is a parent of, that z is a parent of y. So in either of those cases, x is the ancestor of y. So if we say, hey Prolog, got a question. John and Tom, is John an ancestor of Tom? Well, let's look. John is a parent of Paul. John's a parent of Paul. So because John is a parent of Paul, we know that John is an ancestor of Tom because Paul's a parent of Tom. So then we can say yes, and then we can put like kind of like as a comment, recursed once. But then maybe we want to ask ancestor. Isn't an ancestor? Is John an ancestor of Mary? And we can say yes, and we'll put recursed twice. Why does it recurse twice? Because, well, we figure John is the parent of Paul. So there's this case. And so the z is Paul. So then we try the z. So then now Paul is a parent of Tom. So then we change z. So z became once and twice. So z changed twice, and then long behold we see that Tom is indeed a parent of Mary. So then that z linked John and Mary. So thus we can conclude that John is Mary's ancestor. Alright, so now we've got requests. Excellent. Yes, in answer to Alexander Reynolds' question, essentially the order does not matter. The order does not matter. These ancestor functions, as long as they are present in the database, in the Prolog database, Prolog can make inferences using them. So their order does not necessarily matter, as long as they're both there. And here's why. The reason why they both have to be there is because this is the base case. This is terminal. If this is not there, if that's not there, you get infinite recursion, and you'll never resolve. But if this is there, then eventually you can conclude that z will collapse down to just a base case of parent. So this base case, see how easy recursion is in Prolog? You just write your base case. I define ancestor as a parent, but it could also be this. So then if it doesn't match the base case, then it will try to resolve it to the recursive case. And it will keep doing that. It will keep doing that until it can't resolve it anymore, until it goes through all the options and it realizes, oh, in all the options, this base case never comes up. And so it terminates. So that works. And that's a very easy way to do recursion. Going back to Chris Harn, he asks, is it possible to see an example based around creating a list? Yes, we can do that. That's a really easy solution. So we'll just look. Let's do real quick. Let me pull up my notes. Leave that on my screen for a second. And what we'll say, let's see, let's take a look. Leave that on my screen for a second. Let's see. All right. And now I'm going to clear it, and now we're going to do a list example. Okay. So a very common data structure in Prolog is a list. Lists themselves have the following syntax. They always start and end with square brackets, and each of the items they contain is separated by a comma. So here's a simple list. So that's whoa, heads up. There we go. That's a simple list. So that's a very simple list. And Prolog, it's important to note that Prolog has a special facility to split the first part of the list away from the rest of the list. So you've got something that represents the first part of the list, which in this case would be just the item entry A, and that's called the head of the list. There's also the rest of the list, which would be a list itself, B, C, Freddy, A, variable, apple. And this is called the tail. So what we can do cool stuff with this. We could say something like, if we have first, second, and third, and we say it equals A bar B, then essentially what we're saying is that A equals first, and B equals a list that contains second and third. For convenience, I'm going to copy-paste this. There we go. So that's one way to do it. So now, using a list as an example, we have example lists. Let's say if we have, something important to note, that is the empty list. It's important because it is a list, but it contains nothing. Since Prolog is not vectorized, Prolog is not a vectorized language, like MATLAB or R. So you could see, because it's not vectorized, you can actually have empty lists. It's possible. So now, if we do, we can unify our elements like so. We can say A, B, and C, a list of A, B, and C, we can say it unifies like so. And then we can say that A unify, and I'm not actually going to do this. Let's do a U operator. And then we'll say that A, now this is not actual Prolog syntax. We're going to get to that. But right now I'm just going over the logic, the basics. So A unifies with H bar T, where H equals A, and we know the comma means and, so we can use the comma where H equals A, and T equals that. So this is important. So when you do a unification or a splitting, an intersection of a list, what you notice is that, let's say the list has one entity, well then when you split, that one entity will be the head, not a list type anymore, it will just be a single entity component, and then the tail will be a null list. So it will be an actual list, just nothing in it. Now it's important to note that A, B, and C will unify with A and T where T is equal to BC. So then when you do a union, when you use the actual first and rest operator on a constant, then it will actually, it's like a switch. It will take it out or put it in based on how you use it. So in this case, when we unify A, B, and C with the list A and T, then T will become BC, and A will be removed. However, note that that above value, A, B, and C, note that it does not unify. It does not unify with B bar T, because it's not the first element. So it doesn't unify. It's important to note that the null list doesn't unify with H bar T, and it's important to note that always, the empty list always unifies with itself, the empty list. Always. So those are some rules. Now that we've got that down, let's consider a fact. So let's consider a fact now with lists. So let's say P, and define P. We're going to say that this P is a fact. It takes a list. We've got H bar T, and then it takes H and T. So it has this fact. So if we ask a simple query, if we ask Prolog, hey, if I give you an arbitrary list, A, B, C, X, Y, so now we're using variables, it's important to pay attention, we'll get something like this. That's the output that we'll get. So you're starting to see how that list, how it works. So if we have a rule that says given a list, we're going to use the bar operator to what we call subdivide. The bar operator is a list operator that subdivides the first from the rest, where the head, this is the head, and that is the tail. Thus, since we provided a list, but we gave it variables, it solved for the true case, and if there was more than one true case, then it would have solved all of them. And then it returned yes, because it gave us a true case. Now, suppose we did something like this. Suppose we did P, A, B, C, and suppose we gave X, do we want to constrain it? That is the question. Do we constrain it or do we leave it free? Well, perhaps we will do this. Perhaps we will say we will pass it B, and then we'll just leave Y unconstrained. So let's pass it B and let's leave Y unconstrained. So what's going to happen? Well, now we've constrained X to be B, but we can't, that's not the first element of the set. We can't remove it. We can't do it. So ironically, so then this will say, it will say no, because there does not exist for the variable Y, which we expressed in caps, there does not exist a valid list that will also correctly decompose A, but because we want B as our starting element. That won't work. However, this might work. This might work. Very good chance of this working. If we do that, then it's very possible this will either return, this will do one of two things. This is something you'll have to compile and verify in Prolog for me, since I am short the compiler, but I'm pretty sure that either one of two things are going to happen. Either this is going to happen where it will say, oh, I can do that, y equals the list that contains C, and then it will say yes. That's one option. The other option is that it will not be able, the other option is that it will be an error. The reason that it will be an error is because the head, up here in our rule, we define the head to be H, and the T to be the tail. So head is H and T is tail. The head, by definition, is a singular element. It may not be aware that this, as a singular element, can be decomposed into the first bit of the list. So if you want to run that as a test, that would be good. That would be very good, very healthy to validate. However, there's some things that we can make easy for you. There's some clarifications I can make that will make deriving that much easier. So if we have A, let's say we have A, and we have X, and we have Y, the response will be as follows. X will equal A, Y will equal the null list, and the response will be yes. In addition, if we query if we query an empty list on X and Y, the response will be no. Because once again, you cannot unionize that. That does not get unionized. So this is all logic that we're studying here, and this will give you a much better sense of how to, how to properly manage your lists. Okay. All right, so let's go ahead and open the floor again to questions. All right. Well, last call for questions. Oh wait, I see Alexander's typing. Let's see what he's got to say. Ah, correct. Alexander, that is correct. Essentially, you are correct, and I will validate your correctness. To validate your correctness, essentially, and I would revise it to what are possible tails, because sometimes, depending on the variables you leave blank, sometimes there's more than one acceptable solution. If there is, Prolog will find it. If there's more than one acceptable solution, Prolog will find it. If not, then it only returns the one. And you can reasonably expect, yes, Chris, the tail is BC. And there's no other tails. That is a reasonable expectation. That is the only possible tail given this problem. Remember, when a variable is left free, when you let a variable be free, all of the possible values are found. Good. So, any other questions? That is a reasonable expectation. That is the only possible tail given this problem. Remember, when a variable is left free, when you let a variable be free, all of the possible values are found. Good. So, any other questions? Cool. All right, I'm going to do an in-depth raid on my email, and we're going to call it a night. Remember, if you've got questions Prolog related, especially compile questions, make sure you screenshot the error for me and you send me code. And that'll do it for tonight, guys.